Welcome to Premier Podcast number 119, and today we're talking about the aerodynamics of tandem F1 cars. So in the last podcast, in 118, we looked at the aerodynamics of just one F1 car on its own. Now we are looking at the effects of the upstream F1 car on the downstream one and vice versa, and how the distance between the two affect each one's aerodynamics. So for example, the lift and the drag production. And to look into this, we're going to look at a paper called Aerodynamic Study of the Wake of a Formula One Car. And this is the same paper as we looked at in podcast number 118. You can find it in the link in the description. And if you want to watch the video to this, you can also find it on Spotify and or our YouTube channel. And on our YouTube channel, you'll find other little goodies. So let's pick up where we left off in the last podcast. We finished the aerodynamics of just a single F1 car. Let's look at the aerodynamics of both now. So under wake flows. So in figure 12, they show the comparison between the values of the lift area under wake flows and under free stream conditions. So in other words, the amount of lift that the car is producing when it is closer to the vehicle, to the upstream vehicle and downstream of the upstream vehicle, and comparing that to the free stream condition. So the free stream condition, the lift area that's being produced is about 3.45 about, so it's quite high. But when we are under a wake flow, so in other words, there's a wake from the upstream car hitting the downstream car, the downstream car is now producing much less drag. So let's talk about that. So 4 different situations are studied, which differ in the distance established between the two cars. So 0.25 times the length of the car downstream, all the way to two car lengths downstream. Figure 12 to 15 show the evaluated parameters of the second car, the follower car, and table 5 shows the percentage of change between these respective values. So in figure 12, the effect of the distance of the downstream car from the upstream car on the lift area is very clear, and the relationship is actually linear. So in effect, the further downstream you go, the more lift the trailing car will produce. What's more, even at 2 car lengths downstream, the lift area still only is 2.5, whereas just one car in a free stream flow yields a lift area of 3.5. So even at 2 car lengths downstream, you've dropped the lift coefficient by about 30%. Oh, sorry, the lift area by 30%. Not exactly the coefficient. The lift area is the lift coefficient times the cross-sectional area of the car, which is a measure of the lift that's being produced by this particular car. And all we need to do is times it by the dynamic pressure to get the lift in total. So it can be concluded that the wake from the upstream car is very detrimental to the downstream car's lift production, or downstream downforce production, I should say. This means that as the downstream car approaches the upstream car, the speed at which it can corner drops dramatically because it loses downforce. So you lose friction, which means you can't go around the corners nearly as fast. And that makes it harder and harder for it to overtake the upstream car in the corners. But in figure 13, we now have the drag area plotted with the distance between the two cars. So it's not actually entirely bad that the lift coefficient has, or the lift area has dropped, because figure 13 shows that as the downstream car approaches the upstream car, the downstream car's drag coefficient also drops the drag area as well. That means that on the straights, it can go faster and stands a greater chance of overtaking. It's just that the wake of the upstream car can really just changes when it changes the amount that the car can overtake the other car in a corner. So in other words, when you are very close to the upstream car, you stand a greater chance of overtaking it on the straights compared to in the corners. So this result is not entirely surprising because it is very common for racers, not just in automotive racing, but all racing, for racers to use the slipstream of the upstream person. So that is a well-known way of reducing your drag and allowing yourself to either increase your speed or reduce fuel consumption. So for example, in that movie Talladega Nights, they use this move called the shake and bake, which is where they slingshot each other around each other through using each other's wakes to reduce their drag. So what happens is one car goes behind the other car, and because the drag of the downstream car has now dropped, it can speed up, and then it can just zip around the upstream car much more easily. Now that's on a NASCAR type circuit, which is a very straight, and you need straights to do this. In corners, that's not really the case, as we've seen here. The lift area drops, which means that the downforce drops, which means you can't corner as quickly. So table 6 shows a hypothetical situation on the main straight, of Circuit de Barcelona, where the power and the energy that are required to overcome the different situations are evaluated. And it has been assumed that there is a distance of 1 kilometer and a car speed of 50 meters per second along the whole straight. So this is quite amazing that it shows the lift area at 0.25 times the length of a car downstream drops by 62%, whereas the drag area only drops by 40%. So the lift to drag ratio drops by a total of 37%. So in other words, the car has become less efficient overall. But because the drag coefficient has dropped as well, that is not necessarily a bad thing overall. It just shows that they change at differing rates. Now, table 6 also shows the power required, and this is really amazing. So for a car to overcome the air resistance at 50 meters per second, this F1 car on a 1 kilometer straight, it requires power of 88 kilowatts. Now, if the car is following another car at 0.25 times the length downstream, the power required drops to 33 kilowatts, from 88 kilowatts to 33 kilowatts. That's a massive reduction. Now, at 2 car lengths downstream, the power still drops from 88 kilowatts to 67 kilowatts, but you can see from 2 lengths to 0.25 lengths, the power required drops by half. That's a massive power reduction. So the increase in the front balance which occurs on this enables a short but rather interesting discussion. So it is known that the weight distribution of an F1 2017 spec car is around 45.5% on the front axle. So the car is not supposed to exceed this 45.5% on the front balance, as it may lead to stability concerns. So what this means is that the car cannot be like front loaded. And what's happening here is when a car is traveling downstream of another car, it is more front loaded just from the aerodynamic forces. It's pushing the air forward. So the center of pressure, which by definition is such where the total sum of pressure fields acting on it should always remain behind the center of gravity. This can be explained as the yawing moment of the aerodynamic forces counterbalances the steering of the driver and therefore stabilizes the car. On the other hand, if the center of pressure is ahead of the center of gravity, then the yawing moment increases the side slip angle and produces instability. As the obtained results show, the front balance of the second car adopts always values that are greater than 45.5%. This implies not only a reduction in the stability and the performance of the car, but also a more challenging approach when driving the car. It means that it's more easily to spin out, and there's also safety issues. And also the front tires will start to wear more. So in figure 18, they show the streamlines of the velocity. So figure 18 for 2 lengths downstream shows that the magnitude of the velocity is somehow similar to the one of the free stream flow. Let me zoom out a little bit so you can see. Oh, I think you can see this pretty easily. So at 2 lengths downstream, the magnitude of the velocity is a little bit similar to the free stream one, but a little bit lower overall. However, the end plates and the wingtip elements are still useful for redirecting the flow towards the rear. As the distance is halved, so to 1 car length downstream of the upstream car, the velocity of the flow is reduced and the front wing loses its capacity to govern the airflow. But it is not until the cases of 0.5 lengths downstream and 0.25 lengths downstream that the front wing is fed by really low kinetic energy, and that leaves a notably inoperative situation. The effectiveness of the generation of vortices and redirection of the flows is insignificant. So is this a big deal? If we have the front wings and we have very low energy flow hitting it, is that a big deal? Well, yes, it is, for a few reasons. So obviously, we all look at the front wing and we think, okay, that's for producing downforce and whatever, but it's also for redirecting flow in certain ways. And in particular, producing vortices that then can redirect the flow more and segregate flows more effectively. So if we have a low velocity flow, so low energy flow, the wings are not going to be producing as much downforce as what we want, but also they're not going to be able to redirect the flow as we'd like them either. So that produces major problems. And you can see in these figures that in the free stream case, the front wing really redirects the flow out away from the car. Whereas when we get to like trailing quite close to the upstream car, the amount of flow that's actually being redirected drops dramatically. So that's a major problem. So table 8 shows the percentage of the changes of the aerodynamic coefficients in the rear wing of the second car as regards to the first car. So shifting to the rear wing, table 8 portrays that the behavior of the rear wing is noticeably different. So the loss of downforce is very notable since the very first distance, so 2 lengths downstream, and it keeps increasing as the slipstream distance gets closer. So in other words, the lift area that's being produced even drops at 2 lengths downstream, and as you get closer to the upstream car, it drops more and more. So at 2 lengths downstream, it's 40% lower than what it should be for this rear wing, and the drag area is also 36.2% lower. Interestingly, the drag area and the lift area sort of reduce by about the same amount as you get closer to the upstream car. So that's quite interesting to see that that relationship and then how they stay sort of in check. So it can be stated then that the rear wing is more affected under the wake effects than the front wing, as the latter seems to suffer less and only under close proximity. At 2 lengths downstream, the front wing was only exhibiting like a 3.6% reduction in the lift area and a plus 3% increase in the drag area. So both of those for the simulation would be within about the error, whereas for the rear wing at 2 lengths downstream, the lift area dropped by 40% and the drag coefficient area dropped by 36%, so a huge amount more. So it shows that the rear wing is affected far more by wakes than the front wings. So in figure 20, we can now see the streamlines of the velocity and the rear wing of the second car at a distance of 0.25 lengths all the way to 2 lengths downstream as compared to the free stream case. So under a normal regime, figure 20 shows that the rear wing works perfectly with aligned flow that is redirected by other aerodynamic devices. But it is possible to see that as the distance is reduced, the streamlines tend to deflect slightly inboard. So this means that the rear wing is not designed just to operate by itself. It's designed to operate in like a conjunction with the rest of the vehicle. So if we not only have the flow going over the rest of the vehicle being slow, it means that it can't be redirected as we like it to be, as we found with the front wing, but also it just has a low flow as well, low speed. And that affects the rear wing. The clear jump in terms of velocity magnitude is produced from cases 1 length downstream to 0.5 lengths downstream, where the flow experiences a moderate deceleration as it enters into the strongest wake region. So this means is as you get closer to the car, to the front upstream car, the flow hitting the rear wing becomes slower and slower. And that's a major problem in terms of the amount of downforce that you can produce, because the rear wings are already like tapped out in terms of like how much they're trying to extract from the flow. And once you get a slow moving flow, the rear wings are not going to be producing as much downforce because the flow is going to separate more easily. So it could be speculated that the rear wing is more sensitive to the direction of the flow than the front wing due to its low aspect ratio, the pronounced curvature, and the massive end plates at both sides. Figure 20, so at 0.25 lengths downstream in figure 20, shows a mixture of velocity flows with very low speed that unexpectedly create an inwash phenomena at the rear end of the wing. This evidences that the whole aerodynamic package of the follower car is predominantly disrupted by the wake conditions. So what about the diffuser though? So we know that the diffuser, along with the rest of the underbody, produces about 60% of the entire vehicle's downforce, as we covered in podcast number 118. What about when we have like tandem cars, one upstream, one downstream? So table 9 reports that the diffuser is a device that suffers the most under the wake conditions, as the downforce loss that is in close proximity to the upstream car is 70%, and the drag can be found to reduce by 57% at the same distance. So let's just break this down a little bit more. So we found that the front wing is kind of affected by the upstream wake. The rear wing is very affected. The diffuser is even more affected, especially at close proximity. So at 0.25 lengths downstream of the follower car, so it's very close, the lift area has dropped by 70%. So the diffuser, which is producing 60% and the underbody is producing 60% of the entire vehicle's downforce, is now being reduced by 70%. Comparing this to the rear wing, the rear wing is only exhibiting about 57% reduction or 58% reduction in the same location. So the diffuser is being affected even more when it's in close proximity. That's really bad. The drag area is also being reduced dramatically by 57% as well. However, the interesting conclusion is that the reduction of the downforce starts from even at 2 car lengths downstream, as does the drag reduction. So we have a 25% reduction in the lift area and a 17% reduction in the drag area, even at 2 car lengths downstream. So as soon as you get even close to the upstream car, the entire downforce and drag of your vehicle is significantly affected. So let's talk about figure 21, which shows the pressure coefficient distribution on the diffuser of the second car at the various distances downstream compared to the free stream case. I'll zoom out a little bit so you can see all these. The top figure is for the free stream case, and then the other figures are for the following cases. So on the pressure side, The results that are presented in Figure 21 again show that the whole low pressure zone is affected from even 2 car lengths downstream and just gets worse as the downstream car approaches the upstream car. So for the free stream case in the diffuser section, we can see massive low pressure in this area. The pressure coefficient is down to even -1. But at 0.25 lengths downstream, you're lucky to get even like -0.6 in certain regions. Most of the regions are like around 0 or -0.2, and some regions are even positive in the pressure coefficient. So that shows the diffuser is completely spoiled in terms of its behavior. And then in Figure 22, we see the streamlines of the velocity in this diffuser section for different distances downstream. As for the streamlines of the velocity, Figure 22 describes how the underbody, and particularly the diffuser, is affected by the wake flow. In free stream conditions, the diffuser is fed by a high energy flow that is redirected by the front wing and guided around the flat floor. Nevertheless, the streamlines of the flow are not completely straight as the vortices management allow for the control of the airflow around the underbody. So Figure 22 at 2 car lengths downstream displays a quite non-disturbed behavior of the airflow as the management is still acceptable. So in other words, even at 2 lengths downstream, the underbody flow is somewhat similar to the free stream case. When the distance is reduced, though, the performance of the underbody starts to worsen due to the flow arriving more disturbed into the diffuser, hence not being able to operate properly. Smaller distances, such as 0.5 lengths downstream and 0.25 lengths downstream, so very close to the upstream car, reflect an underbody region that is fed by a very low kinetic energy and rotational flow. The main reason for the massive downforce losses that are reported in Table 9 is that the underbody is noticeably sensitive to underwake flows, as it works closer to the ground than the front wing. This means that the low energy and highly rotational airflow that may not be compressed around this small area, therefore experiencing a massive performance loss, comes in through here. So let's break this down a bit more. I'll zoom in a bit more so we can see. So when we are in the free stream flow, the air comes from upstream and it follows very nicely in the diffuser. That's what it's designed for. And the flow accelerates quite nicely under the diffuser, which means the pressure drops, and that's what creates that suction to the ground, the downforce. As we get closer to the upstream cars now, so we're in the wake, at 2 lengths downstream, we still do get this acceleration, but in all situations, I can't help but notice there are fewer streamlines. So I'm not sure if they've used fewer streamlines or whether it just signifies that there's less air going through the underbody section. I have a feeling that there is less air going through the underbody section because if you have the upstream car and that has low energy wake, like low energy flow coming off of its wake, that means that less air can travel through the underbody, and when it goes to the underbody, it has a higher pressure, so there's a higher back pressure. So what this means is, let's say we have the underground, like the ground here, and then we have the car itself, which I'm just going to draw crudely. You're trying to shove all this air in this underbody section, but there's this back pressure. It's a high pressure. So some air is going to get through still, but other air is going to have to be forced around and, from the sides and etc. So that means less flow is going to go through the diffuser section, which means you can't get the diffuser working as you'd like it to. What's more, the diffuser is typically curved at the back, and if you have low energy flow, so slow moving flow, there's a chance that the flow won't stay attached nearly as well, and that will result in wakes as well. That results in more back pressure and this bad cycle happening. So I think that not only do we have this low energy flow going through the diffuser, but we also have less flow in general going through, just through continuity. So let's move on from here. So Figure 23 is a nice plot. It shows how the lift and drag of the front wing, rear wing, and the diffuser are all affected with a distance behind the upstream car. And overall, the lift and drag are all negatively affected the closer the downstream car is to the upstream one. The relationships are quite linear too, which is nice, whereby at 2 car lengths downstream, the lift might be reduced by a few percent, let's say, but at 1 car length downstream, the effect is about double that, for example. So the drag of the diffuser as well, for example, let's say at 2 car lengths downstream, we saw that there was a reduction of about 18%. At 1 length downstream, that is now about 30%. So it's almost double. It's quite nice and linear. And that occurs for almost every lift and every downforce and drag component of the front wing, rear wing, and diffuser. So let's look at we have some really cool figures here of how the wakes from upstream affect cars from the car downstream. I'll zoom out a little bit more so we can see the legend. So on the wake side, these effects can easily be appreciated in figure 24, where the second car is affected by a flow that is lower in terms of kinetic energy, so that not only reflects the mass, but also the velocity of the air, as the wake that is generated by the leading car is released far away, disturbing its follower. It is also clear that as the second car gets closer, it inherently enters into a unique wake structure characterized by very low speed flow that ranges from 0 to 10 meters per second. And this is quite alarming considering that the free stream flow is 50 meters per second. So the wake is like not even 20% of the free stream flow. So if you have your car operating in a 10% or 20% of the free stream flow that you expect it to operate in, it's not going to operate as you expect it to because the flow is not going to stay attached. It's not going to move the way you want it to. The vortices are not going to be as strong as what you expect them to be, etc. So it is also clear. So therefore, this results in the air being severely affected and the car being severely affected. It is seen that as the second car reduces the distance to the first car, its wake originates at a separation region that enlarges and becomes evident. Sorry, what they've discussed here doesn't really make as much sense. So I'll try to break this down in like everyday English. So what they're saying here is as the downstream car approaches the upstream car's wake, which is now pretty much a separation zone, is now engulfing the downstream car. So you now have this separation zone, which means that the flow isn't even aligned properly with the free stream flow hitting the second car. That means that the flow control devices on the second car are not even experiencing free stream direction like that you'd expect it to. So it's not going to perform as you want it to, and that's why we get such major differences in the lift and drag productions. So as for the lead car, this is interesting though. It can be noted that, so for the downstream car, it's severely affected, its wake is affected, all the components are affected, but for the leading car, it can be noted that its wake is not noticeably modified in terms of the shapes and contours by the presence of the following car. The aerodynamic coefficients that are evaluated for the leading car experience only a small variation of 3% or less, and that's even when the distance between the cars is 0.25 lengths downstream. Now that's a lot less than I expected it to be. The reason why is because when you look at just general racing, like if you can get two cyclists, for example, or even two cars, the pressure drag of both typically reduce when they get close together, and like the entire pressure drag is shared by both of them together. That's what happens. So to have this front car not affected nearly as much as the downstream car is a little bit surprising. However, it probably has something to do with the flow control devices. So this is not just a bluff body, it's a body that has been streamlined. And that means that the streamlined objects are not really as sensitive to that. There isn't as much pressure drag to begin with, but they're not as sensitive to these downstream effects because the flow upstream is still quite free stream, like still quite nicely aligned. So that's probably why the upstream car is not affected nearly as much as the downstream car, or as much as like cyclists, for example, in tandem, because it's a streamlined body. So the pressure drag for one is much lower to begin with. So we're not getting that benefit. And also the objects are very nicely streamlined as well, and the flow is streamlined as well, like hitting the objects, these streamlined objects. So in figure 25, they have one more figure which is quite interesting. It shows the streamlines of the front car, how they go over the second car with varying distances. One thing that's interesting is that as we go downstream, like the second car gets further and further away from the first car, the streamlines from the first car really just jump over the top of the second car. That means that the car downstream is really just seeing fairly clean flow, not 100% clean flow, but cleaner flow. But as we get closer to the upstream car, let's say 0.25 lengths downstream, the streamlines from the upstream car are now hitting the secondary car. And that means that not only do we have this like chaotic, ugly flow, but also the streamlines are at an angle up, which means that some of the flow control devices are not really seeing a very high angle attack. The effective angle attack is lower now because the streamlines are at an angle up. So for example, the rear wing, let's say you might expect the rear wing to have overall an angle attack of 30 degrees because each element has its own angle attack. Let's just say, to simplify it, let's say the entire wing just has a 30% 30-degree angle attack. But with these streamlines at an angle, the effective angle of attack might only drop to 20 degrees or 15 degrees or even less. So that means that this wing is now operating at a lower angle of attack range, which means that the lift produced or the downforce produced will naturally be lower. Not to mention that the rear wing will also not perform as expected because it's optimized for a 30-degree effective angle of attack, not 15-degree effective angle of attack. So that's another reason why these flow control devices do suffer. So in conclusion, the obtained results here suggest that modern F1 cars are designed and well optimized to run under friction flows. That's obvious because that's what they test them in. But they suffer excessively when running under wake flows. Overall, the aerodynamic loads tend to be reduced when running under close proximity, ranging from 23% to a very significant 62%. In regards to the individual focus that is placed on the different aerodynamic devices, it has been found that the front wing experiences a sudden jump in downforce losses only when it enters the close wake region. So it's like 1 car length downstream or half a car length downstream. On the other hand, the rear wing massively suffers from long distances, so even 2 car lengths downstream, but its losses are way more linear and moderate. As for the diffuser, it is found that it represents the most affected aerodynamic device, and its performance is reduced from 25% even up to 70%. This evidences that the concept of the diffuser and vortex management under the floor becomes critically compromised under the wake flow conditions. The modern performance of ground effect by means of vortex management represents a very unique and complex way of modeling modern aerodynamics, but at the same time, noticeably compromises the performance of the cars when an overtaking maneuver is intended. So in other words, the cars as they are set up are very fiddly. Like when the vortices are produced to manage the flows and where they work very well when you're in the friction conditions. But when you're trying to overtake, the cars are like too well designed for a certain condition, so they break down under other operating conditions, is what they're saying here. So for this reason, it is possible to guarantee that the FIA changes in the current regulations are considered to be adequate and justified in terms of aerodynamic necessities. So if they don't change, then it means that the cars are still going to have a hard time trying to overtake each other. But by making the cars produce a less chaotic wake, which is what the changes were, they allow the downstream car to be able to overtake more easily, which means that the field becomes more competitive. However, it is essential here to comment that the present study presents some research limitations. For example, the CFD methodology was a little bit simplified, and it also requires experimental validation. So that's the end of this podcast. Make sure to like, subscribe, and if you want to get better at theory, for example, in this and or CFD, check out our courses in the description, and I'll see you in the next podcast. Peace out, amigos.